So today I'm going to cover section 3.4. It's about zeros of polynomials. So we're going to apply the rational theorem to find the zeros of any polynomial, the rational zero theorem. What it says is if f of x is a polynomial of degree n, where an is not equal to 0, then P over Q, and if P over Q is a rational zero of F. Then P over Q is given by the formula. It's going to be the factors of A0, which is the constant term, all over P is the factors of A0 and Q is the factors of AN, where this is the leading coefficient, or you can say the leading term. So we are going to use this rational zero theorem to identify the maximum number of rational zeros existing for any given polynomial. So let's solve problem number 1 from our handout. List all possible rational zeros. Of the polynomial f of x equals So this is the polynomial we are given. We have to find all the possible rational zeros. By the previous theorem, we have to find P over Q, where P is negative 15. This is the last term is the P, and the leading coefficient is going to be our Q. So P is going to be all the factors of negative 15. So we have to find all the numbers that can go into negative 15 over factors of positive 4. So that is going to be all the numbers that can go into negative 15 is going to be plus 1, negative 1, plus 3, negative 3. And so I'm putting plus or minus and plus or minus 15 all over. The numbers that can go into Q, which is positive 4, is going to be, they are going to be plus or minus 1, plus or minus 2, plus or minus 4. So now we have to write all the list. That is, you have to divide 1 over 1 and 1 over 2, 1 over 4. So we're going to list all the zeros starting from 1. So it's going to be plus or minus 1. You just write first all the whole numbers in the numerator because we can divide them by 1. So you take 1 and then divide everything by 1. Okay. Next, we're going to take, take 1 and then 3, 5, and 15 and divide everything by 1. That's what I did now. Next, I'm going to take the next possibilities are we take 1 and 1, 3, and 5. Take 1, 3, 5, and 15 and divide by 2. So we get plus or minus 1 half plus or minus 3 halves plus or minus 5 halves and 15 over 2. So we are done with divide everything by 2. Next, we are going to divide everything by 4. So 1/4. Next one is going to be 3/4. And then then 5/4. And then plus or minus 15 over 4. So these are the possible rational zeros. Okay. So let's do another examples. Now, next example, we are going to find the zeros and their multiplicities as well. We learned how to find the zeros and multiplicities. However, we are going to apply the rational zero theorem to find the zeros first. For the function so first I'm going to find the zeros. So when we use the rational theorem, we have to first find the factors of 3 over. So this is factors of 3 over factors of 2. So you have to write all the positive and the negative numbers that can go into 3, which are 1 and 3. And the denominator is going to be 1 and 2 because 2 and 3 are prime numbers. So only 1 and 3 can go into that. So the possible zeros are so you take the 1 and 3, divide by 1. So we get 1 and 3. And then we can take 1 and 3 divide by 2. So it's going to be 1/2 and 3/2. So these are the possible rational zeros. So now we are going to use these numbers to find, we don't know which are going to be our zeros. We learned in last section 3.3 synthetic division. So we're going to take synthetic division and then we're going to find the zeros. However, I would say we can use our calculator to find the zeros as well. So it's going to narrow down our work. We can solve the problem easier and faster. So what I can do is I'm going to put this one on our calculator. So one second, please. So I'm going to I'm going to use the numbers. I'll go back to the calculator later. So I'm going to choose positive 1 and see if I'm going to, I can check if this 1 is the 0 of this polynomial using synthetic division. Remember, when we learned synthetic division, if you get the remainder as 0, then 1 is going to be our possible 0. So let's write all the coefficients here. 2, 1, -5, -1, and 3. So let's divide this using synthetic division. Bring the 2 down. Then you multiply 2 times 1, just 2. Then we are going to add them. So 3. And then 3 times 1 is 3. When we add, we get -2. -2 times 1 is -2. So when we add, we get -3. So I am getting 0 as my remainder. That means this 1 is my 0. So this is our 1 is one of our zeros. So 1 is 0 means is a 0. This gives us x minus 1 is a factor, right? So we got 1, 0 now. Now I'm going to check if negative, I'm going to check 1 again because it might be, the multiplicity might be 2. So you take the last one, the answer, not, you don't have to go to the original problem. So divide this again by 2 because we already did the original problem. So you don't have to check again. 5 minus 2 is 3. 3 times 1. So again, I'm getting 1 as a 0. That means x minus 1 is 0 is a factor. Again, that means it might be of multiplicity 2. We cannot conclude that because we have the degree is 4. So we have to find the rest of the zeros. So I'm not done yet. So the answer what we got is 2. The last row was 2, 5, 3, and the remainder is 0. That means the polynomial is 2x squared plus 5x plus 3. So now we have to factor this to find the rest of the zeros. To solve, we have to set this one equal to 0. Now we are going to use AC method. So A is 2, B is 5, and C is 3. So A times C is 2 times 3, which is 6. Now we have to find the factors of 6 that adds up to 5. So 6, the factors of 6 is 2 times 3. And when we add 2 and 3, we get the B, right? So I'm going to write this polynomial or the trinomial. So we're going to write as, we're going to use grouping. So I'm writing this 5 into 3x plus 2x. Then use grouping to factor. We have learned this one earlier. So you can go back and check your notes. 2x, we are grouping 2x squared plus 3x. The common factor is x. So we can take the x outside. And there is nothing common except 1. So we take the 1 outside. So now if you check 2x plus 3, 2x plus 3 is common factor. So x plus 1 equal to 0. Now set each one equal to 0. And x plus 1 equal to 0. Now we are going to solve for x in both equation. So we get 2x equals -3, divide by 2. So we get x equals -3/2. Then we get x equals -1. So if you go back to our original problem, so our original problem, the degree of the polynomial is 4. So look at the original problem. The degree is 4 here. So we have to have maximum 4 zeros. So we got, in the beginning, we got x minus 1. 1 is a 0. So 1, we got that twice. So the multiplicity is 2. Here we have -3/2 as another 0. And the multiplicity is 1. And -1 is also 0 of multiplicity 1. So I will do another one, number 3. So we have to find the same thing, the zeros and their multiplicities. So for the polynomial f of x equals x to the third minus 2x squared minus 14x minus 5. So we have to find the factors of -5, and there is no one number here. That means there is 1 here. So let's write all the factors. Again, it's always going to be plus or minus, because both positive and negative numbers can go into any numbers. So plus or minus 1. So the only possibilities are, when you write it down, when you list them, it's going to be negative plus or minus 1 and plus or minus 5. So let's try so I'm going to try number 5. Sometimes you can just trial and error. Let's try 5. If 5 is 0, if we get the remainder as 0, then 5 is going to be one of the zeros of this polynomial. So let's see if it works. So 1, let's bring this one. 1 times 5, 3 times 5, 1 times 5 is again 0. So we are getting the remainder as 0. That means 5 is a 0. So the degree is 2. We have to have 2 more zeros. So let's see. So the quotient here is x squared plus 3x plus 1. So let's solve this one by it. We cannot factor this so that we don't get any rational zeros. So we have to use the quadratic formula, which is -b plus or minus square root of b squared minus 4ac all over 2a. So a is 1, 1 is a, b is 3, and c is 1. So when you plug in, this is what we get. So we get x equals -3 plus or minus square root of 9 over 4 over 2. So which is -3 plus or minus square root of 5 over 2. So the zeros are +5 and -3 plus square root of 5 over 2 and -3 minus square root of 5 over 2 and their multiplicities. Everything comes only once, so this is 1, this is 1, and this is 1. So let's go to problem number 4. So we're going to use fundamental the conjugate zeros theorem. Let me write it down first. So if f of x is a polynomial with real coefficients, and if a plus bi, where b is not equal to 0, a plus bi is a 0 of f of x, then its conjugate a minus bi is also a 0. So whenever you get a complex number as a 0, then its conjugate is also going to be a 0. That is what this conjugate zeros theorem says. So we are going to apply this theorem for the next problem, number 4. So let's do number 4 now. I have 1 minus 5 is given as a 0 of f of x. This is given. Now we have to find the remaining zeros. So since it is given 1 minus 5i as a 0, we are going to divide this by 1 minus 5 first. So 1 minus 5i. So write all the coefficients here. So for these, when you have complex numbers as the zeros, it's better we use our calculator when you are adding and multiplying or subtracting complex numbers. So we'll bring the 1 times 1 minus 5i is 1 minus 5i, and use your calculator when you're adding complex numbers. So we get negative 2 minus 5i. Again, you multiply these two, we get negative 27 plus 5i. When you add these two, we get 1 plus 5i, and multiply 1 plus 5i times 1 minus 5i, we get, we have to get 0 as the remainder because 1 minus 5i is a 0. So by factor the conjugate theorem, 1 plus 5i is also a 0. So we know that so by conjugate 0 theorem, 1 plus 5i is also a 0. So now we can divide this by the answer. You have to divide only the answer to get the next 0. Okay, so I'm going to take this quotient here and I'm going to divide that by 1 plus 5i. So bring this one down. 1 times 1 plus 5i is negative 1. Negative 1 times 1 plus 5i is opposite, which is negative 1, negative 5i. So they two get cancelled. So now we are left with 1. The quotient is going to be x minus 1. This is our quotient. X from here, it's going to be, this is x, this is constant. So we get x minus 1 as a factor. So set this one, set it equal to 0 and solve for x. So we get x equal to 1 is the third 0. And this is polynomial of degree 3. So we got 3 zeros. The zeros are we have x equals, sorry. The zeros are 1, 1 minus 5i, and 1 plus 5i. So I'm going to show you next example, number 5. We are given x equals negative 1/2 as a solution. Solution also means 0. So 1 solution 2. Now we have to find the remaining solutions. Again, remember the solution, the word solution means zeros or x-intercepts or the roots. So all the 4 words are the same. So x equals negative 1/2. So we have the degree is 4 here. So we are going to have maximum number of solutions, 4. So the one solution is given or 1 0 is given, which is negative 1/2. So we are going to apply the rational theorem. So let's first write all the possible rational zeros. It's going to be factors of negative 9 over factors of 2. which is going to be plus or minus 1, 3, and 9 over. So the zeros are these are the possible zeros. Now we already got the one of the zeros, -1/2. So let's use that 0 to divide the polynomial. It's given x equals -1/2. So let's as a solution. So let's divide this polynomial by -1/2. So that means we have to get 0 as our remainder. So bring this one down, multiply. So we get -1 and we get -2. Multiply -2, -1/2, we get 1. And then we add 18. 18 times half is 0. 0 times, sorry, I am sorry. This is 18 times -1/2. That's why I'm not. Okay, so it's going to be -18. -18 times -1/2 is +9. So we are getting 0 as the remainder. So we're good. Now I have to find the next one. So from the possible zeros, let's try 1. You just trial and error, or I will show you at the end how to use the calculator as well. So 2 times 1 is 2, 0. 0 times 1 is 0, so 18. 18 times 1 is 18, so yes, it works. So that means we got our second 0 as well. So these zeros are 1, -1/2, and let's take the polynomial, this one. This is constant, this is x squared. So we have 2x squared, 0 times x is 0, plus 18 is equal to 0. So now we have to solve this problem. We have to get the x by itself. So let's subtract 18 both sides. So we get 2x squared equals -18 divided by 2. So we get x squared equals -9. So take square root both sides. And remember, we have to put plus or minus. So x is going to be plus or minus 3i because we have negative inside. So the solutions, we got the solutions now. -1/2, which is given, and 1 is 0 solution, and 3i and -3i. So this is our final solutions. So next problem, number 7. Sorry, number 6. We have to find a polynomial f of x of lowest degree with zeros of 3i and -2. Sorry, it's +2 of multiplicity 2. Here the multiplicity is 2. So we know that if 3i is our 0, -3i is also our 0. Okay. So possible polynomial is going to be f of x equal to. So you have to write as a factor. So 3i is a factor, mean x minus 3i. And x minus 3i is a factor, means x plus 3i. I mean, 3i is a 0, means x minus 3i is a factor. Negative 3i is 0, means x plus 3i is a factor. And 2 is a factor. 2 is a 0, means x minus 2 is a factor of multiplicity 2 with power 2. And we have to put the constant because we don't know the value of the constant. So now you can multiply these two, so we get x squared do the FOIL. And these two get cancelled, so we have 8 times. And do the distributive property again, so we get the final polynomial like this. So this is our final answer. So now I'm going to show the calculator. Sometimes if you want to just find the zeros of a polynomial, we can just enter the polynomial on our calculator. So I'm going to take problem number 3, which we have solved. So I'm going to enter that on my calculator. Okay. Okay, so let's set the windows here. So now I'm going to enter the equation. So problem number 3, I'm entering the polynomial x to the third minus, sorry, my, oh, it's, sorry. It's so hard to use my calculator on my from my iPad. To x squared minus 14x minus 5. So graph this. And this is how the graph looks. And then we're going to access the table, second graph. And if you look at the graph, the table, I have 5, 0. That means 5 is a 0 of this polynomial. So that is exactly what we got when we were solving the problem. So that is what I was going to show you on my calculator.